Greetings. Back to Math 3B, Calculus 2, Section 11.3, the integral test for series. I want the class to review the first page of this worksheet. Hopefully you have read or reviewed the PDF files. And here we go. Let's look for the definition or the rule set for the integral test to determine if a series will converge or diverge. Okay. So we've got some criteria that we have to verify if we're going to be allowed to use the integral test to see if a series converges or diverges. And keep in mind, we are, over the course of this chapter, we are developing a list of series convergence and divergence tests. So far, we know that we have the geometric series test. If your series takes the form AR to the N, then you can use the geometric series test. Then we also have the test for divergence, which is only a test for divergence. It's not going to tell you if a series converges. And that states that if your entire series expression does not go to zero, in other words, if that limit as n goes to infinity of your a sub n does not exist, or goes to positive or negative infinity, or goes to a limit that's not equal to zero, then you can say that your series diverges. And now we're moving forward with the integral test, and here we go with that. So we've got some criteria. F of x agrees with every output of your expression a sub n. So you've got f of n equal to a sub n. And we have that here in our definition. We also have that the f of x function is a continuous function. It's also positive and decreasing on the interval from 1 to infinity. So these are the two criteria. Positive, f of x has got to be bigger than or equal to 0, right? For n bigger than 0, right? Because we're only concerned with the values of x that are bigger than 0, but really the values of 1, 2, 3, 4, 5, 6, 7, the natural numbers. But we also need to verify that our function is decreasing. And there are a couple ways of demonstrating that. So that's part of the work that you will do in being able to use the integral test. You'll have to verify that your expression a sub n is positive for all values of the natural numbers, and you'll also have to verify that a sub n is actually decreasing, and we'll get to that in a second. Then what is the conclusion that you're allowed to make? Well, you have to make an extra calculation, and that involves calculating an improper integral. So I refer you back to section 7.8 on that. And here's what it says. If the integral from 1 to infinity of f of x dx is convergent, then the series is going to be convergent. And if the integral from 1 to infinity of f of x dx is divergent, then your series is going to be divergent. So they either converge together or they diverge together. And here is the general outcome. So let's just go ahead here and see just in terms of what does the integral from 1 to infinity or 1 to n of f of x dx look like. It is precisely the area under the curve here, right? And if we look at an infinite or a finite sum of a sub k, if remembering that your f of n is equal to a sub n, so if I start with n equal to 2 or k equal to 2, and I use this as the height of my rectangle, and remember that your delta area here is equal to length times width because it's a rectangle, and that's going to be f of a sub 2 times delta x, right? And so we are starting with k equal to 2, and we can see that if we do that, that sum up to the value of n here is going to be an underestimate of the entire. It's going to be less than the area from 1 to n of f of x dx. And now looking over onto the right-hand side, if we look at starting at 1 here, if we start at 1 and use the height of that rectangle, we can see that the delta area is going to be length times width again, and our length is going to be the height of that rectangle, and that's going to be f of a sub 1, right? Or f of 1, which is a sub 1. Delta x, and that is f of a sub 1 delta x. And so we could see that any arbitrary one would be f of a sub n delta x. And we can clearly see that the sum here, the entire sum, is going to be bigger than the area under the curve, right? And so that's going to give you the what is necessary, because during this proof, we are going to use the fact that if f of x is positive for all values of x, and it's all, then the sum of the partial sums is going to be increasing. And if we've got partial sums that are increasing, then we have a sequence of partial sums that is increasing. And because we have an upper bound up here, then if we've got a sequence of partial sums that has an upper bound, then we're going to get a convergence. So it is quite interesting to read through the proofs here, but and also if we've got a lower bound, and it's then we've got it's going to be divergent if it is larger than if we've got an integral that is divergent at infinity that is smaller than something than our sequence of partial sums, then we're going to have a divergent sequence of partial sums, and therefore our series is going to be divergent. All right, so let's do some problems that help show you how to work through them and fully implement the integral test. So here we go. Determine if the following series converges or diverge. Okay, so first off, can we use the integral test? And when would you want to use the integral test? You only really want to use the integral test if you're actually able to calculate the integral of f of x dx. So if you've got an expression a sub n that you think, oh, I could integrate that, like using a substitution method or using something quite simple and not something quite so involved, then you could consider using the integral test. Also seeing if you can verify if something is positive and decreasing. So first, that's what we're doing. Can we use the integral test? So A is a sub, or the a sub n positive. In other words, is a sub n bigger than 0? So if we want to take a look at 1 over the square root of 2n plus 1, is that bigger than 0 for all n bigger than 0? We don't really care if n is negative. We're only caring about the natural numbers starting with 1. And we clearly see that 2n plus 1 is bigger than 0 for n bigger than 0, and certainly 2n plus 1 is bigger than 0, so yes. And then we also have that this is equal to a positive number because 1 is positive, and square root of 2n plus 1 is positive, and so we do see that that is positive, and that is going to be bigger than 0. So at this point, I want to add a page here and go over how do we show if something is decreasing. So part B here is a sub n decreasing. There are two options, and we want to see the next page for that. And so option 1 for a sub n decreasing is the direct method. And what is the direct method? We want to show that for all n, and the notation that I usually use for all n is equal to for all n. And that's the logic notation. So we want to show that for all n bigger than 0, a sub n plus 1 is less than or equal to a sub n, right? Because that will say that the very next one is smaller than the previous one. And so sometimes that's easy to show by knowing that the bigger the denominator, the smaller the number, especially when they are provided that the numerators are the same. So that sometimes that's a very simple thing to do. But then the other option is going back to first semester calculus and the extreme value theorem. On a closed bounded interval, f of x, a continuous function and differentiable function, will attain its max and min somewhere along that closed bounded interval, and it could appear at the endpoints or inside. So we could show, and also the first derivative test. And the first derivative test, we can show that the if the function is less than 0, our original function is decreasing. So we want to say show using the first derivative test. And what is the first derivative test? If the derivative is less than 0, then f of x is decreasing. Sorry, we don't need to use the extreme value theorem. We just know that it will exist, or the minimum. So if we've got our a sub n is equal to f of n, so we would just be taking the derivative of f of n and show that it's negative. And so we want to show that f prime of n is less than 0. Good. For all n bigger than 0. And sometimes it's okay if it has to be a number that's a little bit bigger than 1 or 2. And I will show you what to do in that case. So back here, how do we want to, in this instance, show that a sub n is decreasing? I'm going to show using the direct method because I'm going to end up with the same numerator. I don't have any n's in the numerator. So show a sub n plus 1 is less than or equal to a sub n for all n. So a sub n plus 1 is going to be square root of, or 1 over the square root of 2 times n plus 1, and that's going to be less than or equal to the square root of 2n plus 1. And so just looking at the denominators here, I can see that 2n plus 2 plus 1 is bigger than or equal to 2n plus 1 for all n bigger than 0. And so we have that then 1 over the square root of 2 times 2n plus 1 is less than or equal to 1 over the square root of 2n plus 1. You could cross multiply and demonstrate as well, but it is the larger the denominator, the smaller the number. Right? Okay, so they're both decreasing, but that is not the test. So this is just, can you use the integral test? Good. Can we use the integral test? We had to show that it was positive, and we had to show that it was decreasing. Okay, so now here's the test. Calculate the integral of the f of x dx from 1 to infinity. If in that showing something, your a sub n was decreasing, let's say, for instance, that you wanted for n bigger than 3, for example, then you would use 3 to infinity down here. If it is bigger than 1, then you would just use 1, right? So in this case, we just, in general, want to do the integral from 1 to infinity, but use that 3 to infinity if you need it to be bigger than 3, as an example. So the conclusion that you will make is if that integral is convergent, then your series is convergent. And if that integral is divergent, then your series is divergent. So I don't have a conclusion yet because I'm actually going to calculate the integral. And so here, how do I calculate 1 to infinity of 1 over the square root of 2x plus 1 dx? I'm going to use the substitution method, let u equal 2x plus 1, du is 2 dx. So if I multiply by 2, I need to divide by 2. And I'm going to get that this is equal to 1/2 the integral of 1 over the square root of u du, which is 1/2 of u to the minus 1/2 du. And that is going to give me 1/2 u to the positive 1/2 divided by 1/2. And I can cancel my 1/2s with each other. And so this is going to be equal to the square root. And if I back substitute for 2x plus 1, I'm going to go to 1 to infinity. And I'm going to end up with, that's going to be 2 times the square root of infinity, because 2 times infinity plus 1 is infinity, minus the square root of 3. And that's going to be infinity minus 3. And that's going to be infinity. So that is divergent. So, conclusion here, that my series diverges by the integral test because my improper integral diverged. Good. All right. So there we have it. We have to, so in order to implement the integral test, when do you want to use it? You want to use it when your a sub n here, and don't forget that your a sub n is the entire expression. So if that is easy to integrate, and then if you can show that it's positive and decreasing, then you can employ the integral test. And what is the test? You calculate the improper integral, and if that integral converges, your series converges, and if that integral diverges, your series diverges. All right. So you can try these. We can try that as an example. So we can use the integral test to expand and provide another p-series test. So this is another test for convergence that we can add to our tool bag. And this states, and this can go back to, if you review section 7.8, this uses one of the theorems that says if the integral of 1 over n to the p, that is an improper integral. If p is bigger than 1, then it converges, and it will diverge if p is less than 1. So this is going to be a very popular test to use with the future comparison tests. So please read through the, and that's just known as the p-series test. So some of these are quite simple. Use it as an example of how to use the p-series test. Here, I recognize that the k is the variable, and that is our variable here. So this is our number p. So p here is equal to ln of 2, and if you calculate that on a using a calculator, that's roughly equal to 0.693, and 0.693 is less than 1. So by p-series test, because our series takes the form of 1 over n to the p, as n goes to 1 from 1 to infinity or greater than 1, this series diverges. And that's the work that you need to show there. Here, we might need to calculate or manipulate this expression a little bit more. So we have 4 over the cube root of 8 times the cube root of k, right? Because we can use that rule of radicals. And the cube root of 8 is 2. And that is, and the cube root of k is k to the 1/3. And that's going to equal 2 over k to the 1/3. And we are using the variable k, and starting from the beginning, this was k equal to 5 to infinity. So because we have the same variable, k and k, and so this 1/2, our p here is equal to 1/2, and 1/2 here is less than 1. And so conclusion, this series diverges by the p-series test. So one more thing in regards to the integral test. If your series that you need to determine the convergence or divergence of satisfies the criteria of the integral test, then you can use this tool to figure out how much you're off by. If you wanted to, if you've got a convergent series, if I wanted to approximate the sum of that series, I'd start adding up the terms of the series. So I'd start calculating some of the partial sums. So if I'm going to do some partial sums, I'm going to add another page here at the end down here, and I'm going to talk about convergent series. So if I suppose that my series a sub n equal 1 to infinity converges, right? And the series a sub n applies to the integral test, or the integral test applies, then convergent implies that the sum of the series is going to equal S, where S is the sum. It's going to add up to a finite number. Well, a partial sum is the sum of the first n terms. And so that's going to equal a1 plus a2 plus a3 plus dot 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 plus a sub n. That's S sub n. Well, what is the remainder? Your R sub n is the remainder of the sum S. So what is R sub n? Then you're just going to continue adding a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 plus dot 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 forevermore. So we have here that S, the sum of the series, we have that S here is equal to the partial sum plus R sub n. So S sub n is your estimate for S, right, for the total sum. And R sub n is going to be known as your error. Okay, so backing up here and looking at this integral test error estimate, you can figure out, like, I'm going to estimate the sum of this series, and it could be within an application that you're working with in the real world. And you can say, well, how much might I be off by? And usually in figuring out how much you might be off by, you want to be using the right-hand side of this. But what does this say? It says, suppose your function agrees with every output on your expression a sub n, where f is continuous and it's positive and it's decreasing. That's basically saying the integral test applies. And a sub n is convergent, and you can verify that by calculating the improper integral. Then if your R sub n equals the sum of your series minus the partial sum, then we have that your remainder is no more than the integral from n to infinity of f of x dx, and it's bigger than n plus 1. So you actually have a range of how much you would be off by, which is kind of nice. So you can figure out how accurate you are. And this goes back to the area under the curve as we mentioned before. So you can modify that by saying this is just S sub n plus R sub n, and just using that R sub n is less than or equal to n to infinity, bigger than or equal to n plus 1 to infinity. If I am just adding S sub n to all sides, you can see where that is going. So I can actually figure out a range and say if I just add the first 3 terms, how much would I be off by? So if I suppose that n is equal to 3, then I know that my sum would be less than or equal to 3 to infinity of f of x dx. And it's going to be bigger than 4 to infinity of f of x dx. And that's pretty nice that I can figure out a range of values of what my actual sum will be, which is kind of good. And then we have some other and that's what we can use in these examples, which I will likely go over in office hours, and I might fill out for you just in terms of notes, just to keep this video short. But we can figure out other things like how many terms are needed to approximate the sum by more than 10 to the negative 3. But I will stop here, and I will see you in a bit.